Have you ever stopped to think about a simple refrigerator magnet? It's a small, unassuming object. You probably have several on your fridge right now. They hold up postcards, shopping lists, or your child's latest masterpiece. But in that simple act, something truly profound is happening. That tiny magnet is performing an incredible feat of strength. It is locked in a constant battle with an entire planet. The whole of the Earth, all 6 sextillion tons of it, is pulling down on that little paperclip with all its might, and yet, the magnet wins, effortlessly. This simple observation reveals a deep and unsettling secret about the universe. We think of gravity as a powerful, inescapable force. It keeps our feet firmly on the ground, holds the moon in orbit around the Earth, and governs the majestic dance of galaxies across cosmic scales. The universe, as we currently understand it, is governed by 4 fundamental forces. These are the rules of the game, the cosmic puppet strings that pull on everything from the smallest particles to the largest galaxy clusters. There is the strong nuclear force, the titan that binds protons and neutrons together inside the atomic nucleus, overcoming their intense electrical repulsion. Then there is the electromagnetic force, the one responsible for the magnet's trick. It governs electricity, magnetism, and light. The weak nuclear force governs certain types of radioactive decay, a process that is essential for the sun to shine and plays a crucial role in the cosmic alchemy that forges the elements. But then there is gravity. Gravity is the outlier, the distant cousin who barely seems related. When you compare its intrinsic strength to the others, the difference is staggering, almost beyond comprehension. It is weaker than the weak force by an enormous margin. It is a whisper so faint that it is a miracle we can hear it at all. To truly grasp the scale of this problem, let's put some numbers on it. Physicists have ways of measuring the intrinsic strengths of these forces. Imagine you have 2 protons. The electromagnetic force will try to push them apart. The strong nuclear force will try to pull them together, and gravity will also try to pull them together. The electromagnetic repulsion between those 2 protons is about 10 to the 36th power, times stronger than their gravitational attraction. That's a 1 followed by 36 zeros. If the electromagnetic force were the size of the entire observable universe, the gravitational force would be smaller than a single atom. This isn't just a small difference. It's a colossal, mind-boggling discrepancy. This is what physicists call the hierarchy problem. This vast gap in strength is deeply troubling to physicists. Nature usually doesn't do things in such an arbitrary way. The hierarchy problem breaks this expectation completely. It suggests that either our understanding of gravity is profoundly wrong, or there is some new physics that is artificially making gravity appear so weak. To understand why gravity's weakness is such a problem, we need to appreciate the theory it clashes with. This theory is called the Standard Model of Particle Physics. It is, without a doubt, the most successful scientific theory ever created by humanity. For the last 50 years, it's been tested with relentless precision, and every single time it has passed with flying colors. It really is a stunning intellectual achievement. The Standard Model masterfully weaves together the strong, weak, and electromagnetic forces into a single, coherent picture. But one force is conspicuously absent from the party. The Standard Model has absolutely nothing to say about gravity. It's the ghost at the banquet, a force everyone knows exists, but one that the theory simply ignores. The Standard Model contains one very special particle, the Higgs boson. It's responsible for giving fundamental particles their mass, but when we try to calculate its mass using quantum mechanics, we get a result that is utterly absurd. In the strange world of quantum mechanics, empty space is actually a bubbling, seething foam of virtual particles. The Higgs boson is constantly interacting with this quantum foam, and these interactions should make it incredibly heavy. The theory predicts the Higgs mass should be roughly 10 to the power of 17 times heavier than what we measured at the Large Hadron Collider. This is the biggest, most spectacular failure of a prediction in the history of physics. To get the theory to match reality, physicists must assume a miraculous cancellation accurate to about 1 part in a quadrillion. It's like having 2 numbers the size of a national debt cancel out perfectly to leave just a single penny. One of the most radical ideas proposed to solve the hierarchy problem is the existence of extra dimensions of space. We're used to living in a world with 3 spatial dimensions: length, width, and height. But what if our three-dimensional universe is just a slice, a membrane floating within a higher dimensional space? This idea has a solid foundation in theoretical physics. The concept is that the particles and forces of the standard model are all stuck to our three-dimensional brain, like characters drawn on a sheet of paper. But one force might be different. Gravity is not confined to our brain. Instead, it's free to leak out and explore the full higher dimensional space. This would provide an elegant explanation for why gravity appears so weak to us. Imagine warming your hands over a stovetop. If it's sealed, all heat goes upward. But if it's porous with a huge room below, most heat radiates away. This is precisely how extra dimensions could explain gravity's weakness. These extra dimensions could be incredibly small, curled up so tightly they're undetectable. Like a garden hose that looks one-dimensional from far away, but has a second dimension you can travel around up close. Another leading solution comes from a completely different, equally beautiful idea called supersymmetry. It proposes a profound new symmetry between the two fundamental classes of particles. In the standard model, particles come in two types, fermions and bosons. Fermions are particles of matter like quarks and electrons. Bosons carry forces like photons and gluons. Supersymmetry postulates that for every fermion there exists a corresponding superpartner that is a boson. And for every boson there's a superpartner that is a fermion. The electron would have a selectron, the photon would have a photino. This creates an elegant way to cancel out the quantum corrections to the Higgs mass. For every virtual particle interaction that drives the mass up, there's a corresponding superpartner interaction that drives it down, cancelling perfectly. To hunt for answers to the hierarchy problem, you need a machine of epic proportions. That machine is the Large Hadron Collider. Buried beneath the Franco-Swiss countryside, it is the largest and most powerful particle accelerator ever built. The LHC is a 27-kilometer ring of superconducting magnets, designed to recreate the conditions that existed a fraction of a second after the Big Bang. It is a time machine, allowing us to glimpse the fiery birth of our cosmos. Inside this ring, two beams of protons are accelerated to 99.9999991% of the speed of light. Each proton whips around the track over 11,000 times per second. At 4 points, these beams collide head-on. In these violent impacts, new and exotic particles can emerge, particles that may not have existed in the universe for over 13 billion years. Surrounding these collision points are gigantic detectors like ATLAS and CMS. These are cathedrals of science, built on a scale that dwarfs multi-story buildings, filled with the most sophisticated electronics imaginable. They act as three-dimensional digital cameras, taking hundreds of millions of snapshots per second, tracking every particle produced to reconstruct what happened in that fleeting moment of creation. Scientists at the LHC are hunting for new particles predicted by theories like supersymmetry and extra dimensions. If supersymmetry is correct, the LHC should be producing superpartners, squarks, selectrons, and photinos. Physicists sift through petabytes of data, searching for faint signals amidst background noise. They're looking for a slight bump in a graph, unusual events that don't fit the standard model. As of 2024, no definitive evidence for supersymmetry, extra dimensions, or other new phenomena has been found. This has led to what some call a crisis in particle physics. But this is not a failure, it's a vital clue. The absence of evidence is forcing physicists to be more creative, to explore even more daring ideas in our quest to understand gravity's profound mystery. We have traveled far from a simple magnet on a refrigerator door to the frontiers of theoretical physics. We started with the observation that the force holding galaxies together can be defeated by a tiny piece of metal. This led us to the hierarchy problem, gravity's incomprehensible weakness compared to the other forces. It's not just a curiosity, it's a profound puzzle challenging our deepest ideas about the universe. The weakness of gravity is one of the essential conditions that allowed our universe to exist and persist long enough to foster complexity and life. Understanding its origin is part of understanding our own cosmic story. Are we beneficiaries of an extraordinary accident, or is there a deeper principle that ensures the universe is a suitable home for beings like us? Solving the hierarchy problem is about finding our place in the cosmos. As of today, we stand at a crossroads. The LHC has mapped known territory but hasn't found a clear path beyond. The universe is more subtle than our theories anticipated, and its solution will likely be more profound than we've imagined. The hierarchy problem remains one of the greatest unsolved mysteries in science. It's a window to deeper understanding. The search represents the best of human spirit, our relentless curiosity and unwavering faith that the universe is ultimately understandable. The next chapter is unwritten, and the thrill is in not knowing how it will end.